Electrostatics, electrostatic fields, series on electromagnetic field theory, lecture number 1.12. The basic problem or fundamental problem of electrostatics is finding field intensity when source distribution is given, because field intensity is able to provide a good lot of information pertaining to fields. In the present session, our focus is on finding field intensity in the fields due to various standard stationary charge distributions like infinite straight line charge, infinite plane sheet charge, spherical shell, solid sphere, etc. using Coulomb's law. Here we consider four types of charge distributions: infinite straight line charge, infinite plane sheet charge, hollow spherical shell, inside the shell, outside the shell also we consider field point and try to find out field intensity, and also solid spherical charge we consider field point inside the charge, outside also, and try to find out, estimate the field intensity. The solution procedure involves certain steps, standard steps. They are enumerated here. First step is selecting appropriate coordinate system. It depends upon the symmetry associated with the charge distribution, source distribution. If the source is infinite straight line, cylindrical coordinate system is appropriate one. In case of spherical shell or solid spherical charge, spherical system is the appropriate one. It depends upon the symmetry. Then next step is locating the source over the coordinate system. When it is placed properly, appropriately, the solution becomes incredibly simple and easy. Then we have to select appropriate field formula. Depending upon the source distribution, one of the formulas available for line charge, surface charge, volume charge, it is to be considered. If you want field intensity due to an infinite straight line charge, we have to select the formula like E equal to 1 by 4 pi epsilon integral lambda dl by r square r cap. If it is surface charge, formula corresponding to surface charge. So appropriate formula for field intensity is to be selected. Now we consider field intensity. How to find field intensity in the field given by an infinite straight line charge. It is shown here, infinite straight line charge, infinity downwards, infinity upwards. Let us suppose lambda is charge density coulombs per meter at a point P. We are interested to find field intensity. Let us suppose the distance of this point is rho from the charge. Now we do the problems, or we solve the problems. While solving the problems, we follow the steps that are enumerated earlier. Now coordinate system. Out of the three that is there available to us, which one we have to select? We have to go for cylindrical system, because straight line is a cylinder with radius tending to 0. So it exhibits cylindrical symmetry. Therefore, cylindrical system is the appropriate one. And then we locate the charge over z-axis and move this charge in such a way that field point is over xy plane. If we locate in this manner, solution becomes quite easy. The formula we have to select, or we have to use here, is E equal to 1 by 4 pi epsilon integral lambda dl r square by r cap. This is general formula. For the charge over z-axis, dl becomes dz, and r is the distance between source point and field point. It becomes rho square z square. Unit vector from source point to field point becomes rho cap minus z cap by rho square plus z square under square root. Here we can note charge at plus z. Consider small charge, differential charge here. It gives minus z field component at P, which is cancelled by plus z component given by the charge at minus z, leaving behind only radial components. What he is trying to tell is, you consider differential length here. It gives rise to field at P like this. One component in rho direction, another in negative z direction. Consider another charge, differential charge, at the same distance, but at minus z. If this is at plus z, let us suppose this is minus z, at minus z. Consider at minus z a differential charge. This charge gives rise to certain amount of field here, whose direction is. This can be resolved into two components, one along rho direction, another along positive z direction. The point in this para is, this is in positive z direction, this is in negative z direction, and magnitude wise they are equal, so cancellation happens. So we are left with only rho component. This argument argument we can apply for all charge points or differential charges lying over z-axis to find that the field is entirely in rho direction. Z components we need not consider at all. So here is the complete this one. Charges over z-axis, field point is over xy plane. This is rho, this is phi. We consider source point at a distance of z. The coordinates are 0, phi, z. This is differential charge. dq is now lambda dl becomes lambda dz. And substituting all these things, now r is the distance from source point to field point. Already we have shown the expression. So substituting all those expressions for different values in the general expression for E, we will be having E equal to 1 by 4 pi epsilon minus infinity to plus infinity lambda rho dz rho cap by rho square plus z square 3 by 2. Integration is from infinity to plus infinity, minus infinity to plus infinity. Now, as already mentioned, z components do not exist. So we have not considered z component in this expression. Only rho components are considered. That's why rho cap. Minus infinity to plus infinity, that can be replaced as 0 to infinity. So after integration, ultimately we will be getting, substituting the limits and all that, lambda by 2 pi epsilon rho and rho cap. So this is the expression at a point P, which is at a distance of rho from infinite straight line charge. Here in the graph it is shown how field varies with respect to distance. So this is charge distribution. As you move away from the charge distribution, the field is inversely proportional to rho. So field is falling like this. We consider another charge distribution, that is infinite sheet charge. Here is shown infinite sheet charge. One can understand infinite sheet charge comes into picture when we make the radius of a finite circular charge tending to infinity. We consider a circular charge. This is circular charge. It is a sheet charge, circular sheet charge. Radius A. If A tends to infinity, this finite sheet charge becomes infinite sheet charge. It is given that sigma is charge density, coulombs per meter square. Now, coordinate system that is appropriate in the present configuration is cylindrical system. Reason is this sheet is a cylinder with radius tending to 0 and thickness or height tending to 0, radius tending to infinity. Now we locate this over xy plane, charge over xy plane with the field point over z-axis. The formula that is appropriate to the present problem is E equal to 1 by 4 pi epsilon sigma dA by r square r cap. So the integration is surface integral. dA becomes rho d rho d phi, differential area. Distance between source point and field point becomes rho square plus z square. R cap is z cap minus rho cap by rho square plus z square under square root. Two charges diametrically opposite give normal to z field components at P in opposite directions, cancelling each other, leaving behind only z components. What he is trying to tell is, this is the point I want field intensity. Due to this sheet charge, field here, it has only z component. It is entirely in z. Why? Reason is this. You consider a small area here. The charge within this area gives rise to certain amount of field like this. Diametrical opposite, you consider another charge. This also gives rise to certain field. It is like this. These two can be resolved into two components. One along z direction, another normal to z. This also you can resolve into two components. One along z, another normal to z. This normal to z components gets cancelled, leaving behind only z components. So the location of the charge distribution and location of field point over the coordinate system is shown here. So xy plane is occupied by source distribution. We considered a source point. This is source point. This is field point P. R and dq, all those things we have already considered in the previous slide. Now substituting those things here, E equal to 1 by 4 pi epsilon 0 to 2 pi 0 to infinity sigma z rho d phi dz by rho square plus z square 3 by 2. Integration is 0 to 2 pi 0 to infinity. 0 to infinity is over radius. 0 to 2 pi is to cover the entire sheet phi. We considered here, note, we considered only z component. Rho has both unit vector this r cap has both rho and z components, but as already mentioned, rho components gets cancelled. You're leaving behind only z component. That's why we considered only z component. After integration, we are left with sigma by z cap by 2 epsilon naught. So this is the expression when field point is above the sheet. If the field point happens to be below the sheet, here you will be getting minus. So if you consider a sheet, above it is upwards, below it is downwards. Here is shown a graph indicating how field intensity varies with distance. Notice it is constant. It is independent of distance of the point. Nowhere you can find Z in the expression. Of course, Z prime is unit vector, sigma by 2 epsilon naught. Third problem we consider, third configuration we consider is a spherical shell charge. Of course, it is exhibiting spherical symmetry. So appropriate coordinate system is spherical system. Location is place the center of the charge over the origin of the coordinate system. Formula, appropriate formula is E equal to 1 by 4 pi epsilon sigma dA. This is the formula you have to consider whenever the charge distribution is a surface charge. If it is line charge distribution, we have to consider formula that is for line charge distribution. If it is surface charge, sigma dA. Now, it is placed in such a way that the field point is over z-axis. So, we consider a source point whose coordinates are A, theta prime, phi prime. Differential area becomes dA prime is A square sin theta d theta prime d phi prime. The distance between source point field point becomes h square plus a square minus 2ha cos theta prime. What is h? We will see in the next slide. So this is the setup. The shell is placed over the coordinate system with its center coinciding with the origin. We consider a field point over z-axis. We rotate it until field point is over z-axis. Here, somewhere here. This is source point. Source point. Here A is radius of the shell. Theta prime, phi prime. These are angles. dA prime at A, theta prime, phi prime. And here also we can see the source or the charge at A, theta prime, phi prime. It gives rise to certain amount of field like this. Diametrically opposite or radially opposite, we can consider another charge, source charge, which gives rise to field like this. These two fields we can resolve into two components, one along Z, another normal to Z. We can see normal to Z components are opposite to each other, cancelling each other. Ultimately, you are leaving behind only Z component. So other components, we need not worry about other components, because by just mere observation, we can say that they don't exist. So only Z component, DEZ. DEZ means the field due to this differential charge located at A, theta prime, phi prime. That is sigma by 4 pi epsilon integral dA prime by r square cos alpha. Sigma by 4 pi epsilon integral a square sin theta d theta prime d phi prime by r square cos alpha. So E becomes integration for the entire spherical shell. It results ultimately 1 by 4 pi epsilon q by h square. Now notice alpha. Alpha is here. This is alpha. This is alpha. Notice this expression is similar to the expression for field due to a point charge. So field outside a spherical shell is same as field due to a point charge. After adding direction, we will be getting like this. E equal to 1 by 4 pi epsilon q by r square r cap. When the field point is outside the spherical shell. Sometimes you are interested to know field inside also. We can do the same thing, same manipulation, cosine rule and all that, and find E0. So inside spherical shell field is 0. You see here in the diagram, inside, when field point, distance of field point from the center is less than A. That is when field point is inside, field is 0. Outside, it is varying. The relation is inverse distance square relation. Now we consider a solid spherical charge. The difference between previous one and this one is, previous one is surface charge, whereas this one is solid charge or volume charge. The procedure is, we don't solve this independently or standalone problem. We consider it as an extension of previous problem, that is spherical shell charge. What we do is, this is solid spherical charge. We divide it into shells. Each shell gives rise certain amount of field at the field point. That field we have already calculated. It is given by 1 by 4 pi epsilon q by h square. In the previous problem, we calculated. So first we divide this fellow into several shells, and field intensity due to each shell we can write down, we can find out within no time using the expression already derived in the previous problem. But we are interested in field due to the entire solid sphere, charge sphere. So what we do is we add, using superposition principle, we add fields due to all these shells, resulting in field due to solid spherical charge. Addition we need not do, integration takes care of that addition. Okay. The given solid sphere is divided into thin shells of thickness dr, differential radius. The field due to each shell is available, and fields due to all the shells are then added by integration to get field due to entire solid sphere. Coordinate system is of course a spherical system. Location is center of the sphere right over the origin. This is the charge distribution. We consider both field point, both outside, inside also. Outside at a distance of h naught, inside at a distance of hi. Hi is less than radius a. Here rho is charge density, coulombs per meter cube. So this is the charge located over this thing. We consider a thin spherical shell, radius dr at a distance of r. This is field point located at a distance of h naught from the origin. We know the field due to this small thin spherical shell. First we write down, and then that field is integrated over the entire charge distribution. D differential field intensity due to shell whose thickness is dr. It is given by this one. Here dq dr is the charge that is there within this shell. Then E equal to, if you integrate this field expression from 0 to A over the entire charge distribution, we will be getting field intensity due to the total solid spherical charge. So some manipulation, little bit of manipulation is done here, and ultimately what we get is when field point is outside, it is like this. Notice this expression is same as the expression of a point charge. Suppose here is a point charge at a distance of h naught. What is the field intensity? This one only, same as this. Or if you have a spherical shell charge, what is the field intensity at P when P is at a distance of h naught from the center? Same one. So spherical shell field, point charge field, solid sphere field, their expressions are same provided the field point is outside. Inside story is somewhat different. So this is outside. This is the field intensity outside. When it is inside, manipulation is slightly different. E equal to 1 by 4 pi epsilon Q hi by hi square r cap. QHI means, so this is total charge. QHI means you consider distance radius hi. Within this radius, or within this region bounded by radius hi, there is some charge. That charge is QHI. So this is the formula we use. Some manipulation results in this kind of. Notice E equal to 1 by 4 pi epsilon QHI by hi square r cap. This is field. Some manipulation. Ultimately you are getting this. All the formulas so far we have derived, they are placed in a diagram. Please note point charge. For point charge E equal to 1 by 4 pi epsilon Q by r square r cap. Now this is in coordinate free form. He says it is not in any particular coordinate. R is not there in any coordinate. We have x, y, z, rho, phi, z, or rho, theta, phi. This R, capital R is not there. Similarly, come here, spherical shell charge. Spherical shell charge E equal to 4 pi epsilon Q by r square r cap. But this r cap is spherical coordinate. So this formula is in spherical coordinate system, whereas this is in coordinate free form. Okay, that is the difference. The similarity is also there. Form wise they are same. Field intensity is inversely proportional to distance square. Field intensity is proportional to charge. Here also field is inversely proportional to distance square. Field is proportional to total charge over the spherical shell. Come here also it is same as spherical shell, but it is in coordinate form, spherical coordinate system. Small r is there means it is spherical. Capital R there means it doesn't belong to any coordinate system. Similarly, come to second one, E equal to lambda by 2 pi epsilon rho cap. So rho means it is cylindrical coordinate system, inversely proportional to distance. E equal to sigma by 2 epsilon n cap. This is for infinite sheet charge. Here there is no coordinate system. Sigma means surface charge density, n cap means normal to surface. So it is also coordinate. So these two formulas, field for point charge, field for infinite plane sheet charge, these two are in coordinate free form, whereas field due to infinite straight line charge is in cylindrical, whereas this one is in remaining two are in spherical coordinate system. So far we covered certain standard stationary charge distributions to find their field intensities. This is all what I have to share with you for the present.